and we have the very best spokesperson that we can possibly find. Jim Wolfe is the president of Global Policy Associates in Arlington, Virginia, which is outside Washington, D.C. Jim was the president of ASHRAE 2000 to 2001, so he's now a presidential member of ASHRAE. He's ASHRAE's point man on the phase down of HFCs, and it's the very best source of information. Jim has a bachelor's degree in electrical engineering from the University of Arizona and an MBA from American University, and we're very thankful and honored that he's come all the way to Toronto to show us the industry's response to the Kigali Amendment. Jim?
Can I use the keyboard to advance instead of the...
You can use...
Will that do that? Yeah, sure, it works.
Up and down, yes.
Yeah, okay, that's great. Okay, well, I'm very happy to be here, and I've been involved in this issue on refrigerants for over 50 years, and been involved in all the U.S. regulations and laws that affect refrigerants, and been attending the Montreal Protocol meetings since 1988, and attending the climate change meetings since 1993 as an industry advisor. So I've stayed up to date on what's happening in refrigerants. So I'm going to get into the weeds a little bit for you. I have an hour presentation that I'm supposed to do in 30 minutes. So I saw a shock on your face there for a second. So what I'm going to do is talk about how, from a technology standpoint, we're responding, not from a philosophical standpoint. And basically what I want to review very quickly is the environmental policy that's forcing this refrigerant change. Because it was mentioned earlier, we used to have perfect refrigerants, and now because of environmental concerns, they aren't perfect. And I want to compare then also what the refrigerants look like when you compare it to the policy, whether they'll survive. And I want to talk about the future refrigerants. So the starting of this process was the Montreal Protocol, and the fact that it controlled the ozone depleting substances, and it just happened that the CFCs, 11, 12, and the 500, and the 113s, and the HCFCs, 22, and then eventually 123, got controlled under the Montreal Protocol because they had ozone depletion. The other chemicals like the HFCs, like 134A, 410A, and 407C, were not controlled originally under the Montreal Protocol. They were controlled basically under the Climate Change Convention.
This is all in the ASHRAE Handbook of Fundamentals, which you can get if you join ASHRAE.
Yeah, if you join ASHRAE. Yeah, thank you for making this. So the Montreal Protocol is a great protocol in that all the countries are involved. There's penalties if you violate once you ratify it and make it your treaty. It covers the key ozone depleters, particularly from the refrigeration air conditioning industry, and it stays in place forever. So it's great. And it's doing the job, we're solving the problem. Now, the final regulation that was agreed to in 2007, and there have been no proposal to change it since 2007, 10 years later, is over. You see in Montreal in September 2007, there was a slight change for developed countries, 38 countries out of the 201 in the world, that there would be a little more reduction or a little faster phase out, but they retained the basic requirements in the international law that you were allowed to put in new equipment 22 and 123 on the HCFCs. Now, CFCs were all phased out worldwide in 2010, so I'm just really going to address the HCFCs. So 2020, you have to stop putting newly produced 22 and 123 in equipment in a developed country like Canada or in the US. But you can produce for servicing for 10 years. In developing countries, the rest of the countries like India and China and other countries, they have a phase-out schedule that allows them to use them longer, and they can put 22 and 123 in new equipment until 2030, and then they have a 10-year service tail till 2040. But in 2040, no more production of HCFCs, 22 and 123. Now, in the US, we do a command and control process because we don't want to violate the Montreal Protocol. We regulate the worst first, so we got rid of 141B, was foam blowing. Then 10 years earlier, we stopped putting 22 in new equipment, and you did the same in Canada. A service tail till 2020, 10 years earlier than was necessary, but retained the 2020 for 123 for new equipment and servicing until 2030. Now, here's a little more details, a little more in the weeds about the Kigali Amendment. We really have three different requirements. One is for developed countries, 38 countries, the A2. One requirement is for all other countries except for, on the far left, except for 4 countries. the 4 countries wanted a little more time. And basically what happens in Canada and the US, you will take your 2011, 12, and 13 consumption, the average of that, and then you add to that 15% of your baseline of HCFCs, and that gives you your quantity in kilograms or pounds. And then in 2019, you have to be 10% below, which is not really a challenge. That's going to come from automobiles, refrigerators, and whatever. But in 2024, we have to be 40% below. I think that was part of what motivated Environment Canada to put in a requirement on chillers. Because the technology is out there now, we can get the HFCs out of chillers by 2024 or 2025, and that gives us a 40% reduction. We need to take a deeper step in 2029. We need to go to 70% reduction. We have a problem in getting there. Tom mentioned that it's undesirable to use flammable refrigerants. We're going to do the undesirable in the future, and we'll talk more about that. And the reason that we couldn't take any regulation right now on the unitary home air conditioners, anything that uses a scroll compressor, that's a positive displacement type compressor, we do not have acceptable alternatives yet, and we don't have production of those alternatives. So we need more time, and we need time to change the codes to allow their use because they are flammable. And we're going to be talking a little more about that. Now, you'll see basically developing countries don't get their 10% cut until 10 years later. Basically, it's consistent with what we did in the Montreal Protocol on the CFCs and HCFCs, or on the HCFCs. So these are some of the specific requirements. And these specific time levels, particularly for developed countries, were driven by the knowledge of how the technology can progress and how fast we can get out of the HFCs and some of the challenges we have in getting out of the HFCs. Now, skip that one. 10 years after the Montreal Protocol, along came the Kyoto Protocol, and we had a concern with the alternatives for CFCs and HCFCs. Because they are HFCs, and they were controlled under the Kyoto Protocol. It didn't work effectively. It was only for developed countries. It was only going to be 5.2% reduction in emissions, and it didn't work effectively. And so there's a second phase of the Kyoto Protocol, but Canada and the United States was never involved in the Kyoto Protocol. Canada was, but now Canada, the United States, Japan, Australia, New Zealand, they're not going to be in the Kyoto Protocol, and neither are developing countries. It's going to be basically the European countries, and so they're doing a little bit more in that area than some of the rest of us. The main concern there was emissions of HFCs, and it was felt by the Montreal Protocol that you weren't going to get proper attention to the HFCs, which were going to grow from 1.2% to 15% over time. And so the Montreal Protocol, after 7 years of negotiation of the Canadian Amendment, North American Amendment with the US and Mexico, took action to control HFCs similarly to what we did with the CFCs and HCFCs, with a phase down, not a phase out. But let me caution you, the Montreal Protocol originally, even though it was a phase out, it originally started phase out of CFCs only. So the caution is, we get the technology and we make progress. I don't think the delegates from the 197 countries can help themselves but to deepen the phase down to maybe a phase out, except for exempted uses. That's what we expect in the industry will happen. Now, Paris Agreement, how does it affect the HFCs and the air conditioning refrigeration area? Well, it controls the emissions, but it's not going to take a lot of fast action, and it is not a mandatory requirement. It's a second stage of climate change, going from the Kyoto Protocol to a Paris Agreement, which is really a voluntary pledge type system. The goal is to meet 2 degrees Celsius limit in growth of the temperature. Countries have submitted plans. They were originally called Intended National Determined Contributions. Now they're called NDCs because they're in place. Basically all the countries have submitted those, or are going to submit by 2020, for what they'll do between 2020 and 2025. And then in 2018 they'll start planning for what they'll do from 2025 to 2030. There's certain mandatory things you have to do under the Paris Agreement. Like you have to report, like you have to have plans, like you have to update your plans every 5 years. But it does not require that your second, third, and fourth plans are more stringent than your first plan. And they are contributions, not commitments. So it doesn't effectively force the reductions we need. And the current plans only limit the increase in temperature to 3.7 degrees. An increase of 3.7, not 2. There's going to be money available for that. It's gone into effect. The U.S. has accepted it, not ratified it, even though it's considered a treaty. President Trump could decide to pull out, but he'd have to give 3 years notice to do it and do it 1 year later. We don't know what's going to happen, but in October, I think we'll know what we're going to do on climate change. Don't think it will affect the Kigali Amendment to the Montreal Protocol. Don't think it will affect the chiller rules. Europe has some regulations in effect earlier. Those will be strengthened by the Kigali Amendment. Now, there was already discussion of the Canadian rule. I just wanted to point out refrigerant air conditioning, very critical when we look at the technology, because you'll notice for chillers, centrifugal chillers and positive displacement chillers, that on January 1st, 2025, you're not allowed to put in a new chiller a chemical, a refrigerant, that has a GWP above 700. And we'll see in a minute why that 700 was set. Now, that's a little bit different than what the U.S. has done. The date is January 1st, 2025. The U.S. has done January 1st, 2024. Let's harmonize, okay? And that's for all of these refrigerants we've used in the past, which means in the U.S. we're taking action on the chillers. I think that will stand. I don't think it will be repealed. I think it will stay in place. And the industry supports doing that because we have the technology developed. We have the refrigerants developed. We've made the investments. Let's move forward. Now, this is why we got out of ozone depletion, getting out of these chemicals with a high ozone depletion potential. Global warming, we still have relatively high GWP potential. And the question on efficiency, what we've learned, if you optimize the refrigerant in the technology without making other technology changes, 11 was the most efficient, 123 almost as good, and then 12 and 134A. But every time we move from CFCs to HCFCs to HFCs, we lose potential to have the most efficient equipment. And we have to improve the technology to upgrade that. Now, having said that, the CFC 11 was never an efficient chiller compared to what 123 is today, and neither was 12 compared to 134A, because we had not optimized those. The average kW per ton that was in a chiller in 1990 was 0.8. Today we're commonly buying 0.6, 0.54, the lower the better. And we can even do 0.54. So a lot of progress has been made. And we'll make the same progress when we go out of HFCs. And so you can see on this chart, CFCs were bad. Both ozone depletion and global warming, had to get rid of them. We had some choices. Maybe we could go to 22. It has ozone depletion. It's going to be phased out. We go to 123. Got ozone depletion could be phased out. Well, maybe we could use 32. It looks pretty good. Not much GWP. But it's flammable. Don't want to use flammable refrigerants. Didn't want to use 152A in cars for substitute for 134A, although 152A looks like a perfect refrigerant environmentally. Almost perfect, but it's flammable, so we didn't want to use it. So we went to some other chemicals that were non-flammable, but had significant global warming potential. So here's what's happening to us in the industry. Because of the ozone depletion concern, now that didn't go forward like I wanted to. We are going to eliminate all of the CFCs and the HCFCs from our products. And because of global warming, we're going to eliminate 134A, 410A, and 407C. Maybe we could use 32 or 152A. Maybe we could use natural refrigerants, but they have flammability, they have to meet the requirements to make them safe. It increases the cost of the technology 30 to 40%, and we have some efficiency concerns. Now, we could use natural refrigerants. CO2, which has a GWP of 1, base of reference. It could do everything we need to do, almost everything. We could do low temperature, we could do comfort conditioning, but it has half the energy efficiency of 22 and 410A, which we're using today. So it means to get the same efficiency, it's going to cost twice as much, or we can't reach the efficiency levels we want. Hydrocarbons like propane and butane, they're good refrigerants. They're as good as 22. Highly flammable, explosive. Only going to be used in limited applications. You can only use 300 grams of a hydrocarbon refrigerant in a piece of equipment today. That's less than a half-ton size. So it's going to be very small equipment. So you could do it in small room air conditioners, you can do it in refrigerators and some other things, but unlikely you're going to do it in a big chiller in an equipment room. Ammonia is toxic and is flammable. It's being used, but you have to have, it's very expensive to use it. You have to have skilled operators and there's special applications. And absorption is really, water or absorption is not really being used. So we're faced with a situation that we need to use low GWP refrigerants to meet the Kigali Amendment. It means we need to use flammable refrigerants. What happens is we're moving into a realm where the alternatives have low GWP, no ODP, but some of them have flammability. And we're going to talk about some of those. So these are concerns that we now are faced with because we want to maintain our efficiency and our cost. You have to get into flammable refrigerants for medium pressure centrifugals and screws. In other words, they're 2L by the ASHRAE standard 34 definition, which is used worldwide on the category of flammable refrigerant. So it means, do we want a flammable refrigerant in an equipment room with a large charge? And if we do, what conditions do we have? What's the ventilation? What's the identifying that you have a problem? Whatever. So you may have 1, 2, 3, 4 ZE used in some chillers. They're being used in Europe in some cases, but you have a 25% efficiency or capacity loss. Yes?
I just have a quick question. So you said 513 is going to be probably phased out also in Europe. What about North America? Are we leaning towards that as a replacement for the flammable?
I'm sorry, I didn't hear your question.
Sorry, you said for our 513,
yeah,
they would probably be phased out in Europe.
Yeah.
What about North America?
Don't know.
Are they going to be leaning more to that being a replacement for the flammable?
But right now, and what is happening, and let me go on a little bit further how we're going to address that question, because a lot of research is being done right now to make a decision on whether or not we can use these flammable refrigerants. In Europe, they've already decided that they can use more flammable refrigerants. For example, they're talking about hydrocarbons like propane going up to 1,000 grams from 300 grams. U.S. is going to decide through the ASHRAE work, what level we should do, and that will be going in the building codes. And Canada is very involved in that process. In fact, 10% of the members in ASHRAE come from Canada, so there's very strong contribution here. My prediction is that what will happen is for the large chillers over 600 tons, they're going to use low pressure. For the screw chillers and chillers below 600 tons, they're going to use the blends as long as they can, and ultimately if you had a requirement that went below the 573, then you'd have to go into flammable or give an exemption. So we don't know where we're going there. So let's talk about the area where we really have a problem. This is the residential area. What used to be in your home air conditioner, we looked at going out of 22. You're out of 22, you're in 410A. We looked at 3 options, 410A, 407C, and 32. 32 is flammable, so we made a decision not to use that. And 407C, which was almost a drop-in for 22, would fractionate or separate, and if you lost some refrigerant charge, then you'd have to totally evacuate and recharge, whereas 410A, you could just add refrigerant because it doesn't fractionate. So what we did is we went out of these 22 to address ozone depletion, but now we need to get into a low GWP because 410A has a GWP of 2,000. 134A has a GWP of 1,430. Smaller than some of the HFCs, but still significant. So now we're looking at alternatives. So let's go back and look at 32. If we're going to use flammable refrigerants, let's consider whether we could use 32. And let's look at blends. They looked at hundreds of blends, came up with combinations of different chemicals, like a new chemical called YF that is used in auto air conditioners, and then 125 and 32, trying to make it not too flammable, trying to make it compatible with the lubrication systems, maintain efficiency and capacity. And so this appears to be the two strong candidates, and there may be a third or fourth, but at this point, these are very strong candidates. There are a couple others being looked at in various parts of the world. So if you look at the substitute for 22, we went to 410A in part of the world. Some developing countries are still in 22. And we have a blend that can almost drop into 410A, which is the 452B, but it's flammable. It's a 2L. And then we have 32, which is a refrigerant we haven't used much in the past, which is also flammable. Now, interesting situation. Developing countries have to get out of 22 by 2030, right? That's what the Montreal Protocol is. They would normally go into 410A, but now 410A is regulated, and they're eventually going to have to get out of 410A. So what do? Do they leapfrog from 22 into 32 or 452B, or do they invest in 410A and make a change later? And the money that's available under the UN to do it can affect their decisions. and other things can affect their decisions. Well, anybody that's in 410A today can easily convert to 452B. So in the United States and Canada, we can use 452B and almost drop it in the same technology. To go to 32, it's higher pressure, it's a little bit more flammable, so it's going to be a little more of a challenge. But those people that are in 22 are thinking about going straight to 32 because it's a cheaper refrigerant and the technology is a little bit more efficient than 452B. But both of these options are flammable. And what do we mean when we're flammable? Okay, starting out with an A3. An A3 is propane and butane. You aerosol that, put a match to it, boom, right? Don't want that. That's the flammable you're talking about. A1, those are the refrigerants we used in the past, and with those refrigerants, you put a match to the refrigerant when it's aerosol, match goes out. Then we have the in-between category of 2s. It used to be only A2, now we have it in two categories, A2 and A2L, or B2 and B2L. So we have said that let's take that category and let's look at those refrigerants that are less flammable. So if they have a burning velocity of less than 10 centimeters per second, we think we might be able to use them. So what happens with an A2 or an A2L, you aerosol, put a match to it, it burns. And you get a big fire envelope. You take the match away and slowly the envelope comes down. The rate of how fast that builds and how easily it ignites is very important. So that's what we're looking at. We're doing a lot of research on that. Now, if you look at the characteristics, you see that this blend, here's how it looks when it first ignites. Here's how 32 looks. Looks like there's a big difference. But it just so happens if it's flammable and it ignites, it ignites. And they both ignite about the same way, it's just got a smaller flame. So we may come up with the same codes and standards to address that. So here's the challenge that's facing the industry. We are going to be using flammable refrigerants, even we don't want to, Tom. And the transition is likely for the unitary equipment going to use flammable refrigerants. We don't know of anything else. And so we need a better understanding of what the consequences are, how they're going to ignite, how severe the ignition will be, how large a refrigerant charge we can have. And then when we get all that information, we need to translate that into building codes and changes. So a lot of work's being done to be completed this year to where we'll have proposals to the building code that's starting its next version in 2018 to be completed by 2021. And we hope that we can incorporate enough things that we can start using some of these flammable refrigerants. But we're looking at refrigerant charge size based on where it's installed in the type of equipment. It could be different on a rooftop equipment, where it's out in the open air, to an equipment room, to a closet, to a hotel room incremental unit, to a variable refrigerant flow type system. So we have to look at all those things. We have to look at how it will ignite, what's likely to happen in ignition, how severe it will be, how do you install it. On a split system, can you use braze fittings? Do you have to use braze fittings? or can you use flare fittings? Or can you use a mechanical connection? How do you service it? You can't just take a blowtorch in and start working on a flammable refrigerant piece of equipment. So you have to evacuate and purge, and what do you have to do? How do you design your equipment room? A lot of things. So that's going to change ASHRAE Standard 15, going to change proposals to the building code. Once the building code gets changed, then it has to be adopted. We only adopt the building code we adopted 43 states out of 50 in the United States. And it takes 3 to 5 years to do that. So if we get a new code by 2021, it's going to be 2024, 2025 before we have the codes in effect and we can use these flammable refrigerants. So we'll need until 2027, 2028, 2029 before we can get out of all these HFCs. And so you'll be considering that in your regulation in the future. US had a regulation proposed that was going to set a limit on the use of 410A in all air conditioning until they became very knowledgeable in the fact that we have this flammable refrigerant situation. So we're undertaking this research. Here's the research that's undergoing. We identified worldwide 29 projects. We only have funding for 7. So we have $1 million coming from AHRAE, the Equipment Manufacturers Association in the U.S., 1.3 from ASHRAE, and 3 from DOE, and 300,000 from CARB on hydrocarbons. I'm chairing the committee that's doing the research on the ASHRAE 3 projects. We have 64 people on that project worldwide. We have people from the UN, India, China, all over the world involved in that. And we're managing projects that are put out to UL and other organizations that do the research. And all that's in effect, the results will come out for these 7 projects this year. And then ASHRAE has a lot of projects on heat exchangers and things like that.
Sorry, what is DOE and CARP?
Okay, DOE is Department of Energy, U.S., and CARP is the California Air Resources Board.
All right, thank you.
Okay? So, here's the need for the change. The current codes and standards are too restrictive. We need to open them up, but we need to do it with knowledge. Or at least we think they're, that maybe the current charge limit restrictions aren't warranted, that we can go into larger charges. And that maybe we can put a flammable refrigerant in your home air conditioner, for example. We'll decide that. So we need to look at the equipment design, installation, servicing, taking equipment out of service, all of these things. So all that work is really important to be done. So here's what the industry is doing at this point. Did it before the amendment, started some of the work after Europe started regulating HFCs in 2005. That's the time when the chemical suppliers started developing an alternative for 134A for autos. And then we continued to develop things over time and got very active in the last few years. So they have been developing near zero ODP, we're talking 0.005, things that won't be covered under the Montreal Protocol, very low GWP. Certainly, we want to go well below 700. We want to get down at around the 150 range or lower if we can. And we have some alternatives. We want them to be energy efficient and we want them to be safe. Not going to be a problem with chillers, it's going to be a problem with the rest of the air conditioning. Commercial availability of the chemicals started in 2015. There's already equipment being sold in Europe, United States, and Canada that are non-HFC. A couple manufacturers have already announced the ZD component and the blends, and they're beginning to develop products, and it's slowed down somewhat by the quantity of refrigerants being produced. And then we have this research going on. So we have a lot going on, a lot to accomplish in the near future. We've covered that. So here's where we went. We have CFCs in 22, and so then we went to the first generation of alternatives, which was 123 plus HFCs, and now we're going to the HFOs, and we have some challenges with blends. So that's what I wanted to mention to you, and I've got. Yes.
You mentioned that the building codes are going to have to change to adapt the flammable refrigerants.
Yes.
It sounds to me like possibly explosions might happen in these type of rooms. What type of compensating features are you looking at to make the buildings sparse and explosions?
Well, first of all, today, to handle any of these refrigerants, the A2 or the A3, you have to handle them all like a hydrocarbon. And so there are laws that just will not allow you to install equipment beyond a certain size range, charge level. Now, in the U.S., we have the significant new alternatives program, and it specifically approves, and if it's not in that list, you can't do it, where you can use various refrigerants. And so they have approved that you can use hydrocarbons in window air conditioners. They have approved that you can use hydrocarbons in refrigerators. But they haven't approved that you can use hydrocarbon in residential or in commercial. So at this point in the U.S., you could not sell a product unless you were complying with the current hydrocarbon rules. So what we're going to do is, through this research, try to identify how large the charge size can be on that particular piece of equipment. Let's say it's a rooftop unit, and it could be a 5-ton, 25-ton rooftop unit, and it's design it in a way to where you're assured the refrigerant will go to the outside air. Certainly you can have a larger charge, okay? But if you have a situation like a split system where you have a condensing unit, refrigerant circulating over your furnace, and you had a leak, you want to restrict that. So we don't have those answers yet. And I think it's really going to be probably 2024 before we have enough confidence that we're going to start using the flammable refrigerants. And so that we need that time for 2029. A lot of questions. We want to do those 29 projects. We don't have enough money. We have 5.8 million. We need at least another 10 million. We're trying to spread it globally. There's going to be a big event at the Montreal Protocol meeting in Bangkok on a workshop on codes and standards to talk about what needs to be done internationally on the international codes and standards in order to adopt these new refrigerants. So a lot of work. Yes?
As a specified engineer right now, what do you suggest we do? Like for VRF systems, should we still be speccing those, or is there anything we can do? Or?
Well, but I have confidence that with because of our experience with CFCs, with any product you specify today, any product that you can buy, there'll be refrigerant available to keep servicing. So it's not a concern at this point. The only concern is when you're prohibited from that. So the first issue is the chillers. January 1st, 2025, you have to spec something else. It's going to be a low pressure or medium pressure using the blend on medium pressure, and the low pressure has some solutions, and those solutions are already out there. So you already can plan for chillers. But for the unitary, you can't take any action. You just continue to do what you're doing, assume with faith that you're going to have the refrigerant available, or that it can be converted. And some of these, you can convert.
You had mentioned something about the VRF conversion. There's
The VRF?
Variable refrigerant flow?
Yeah. The concern there is, right, and you use brace connection on all those today,
Yeah.
but, if you have a 43-ton VRF system and you have 80 pounds of refrigerant, how much of that can make it into this room if you have an outlet here? And if you have a fire, is it going to be in the ceiling or is it going to be the refrigerant dropping? And that research has to be done, and that's included in all of our research. So my projection is that the VRF is going to be so restricted when we have to use flammable refrigerants, there's going to be very limited application. But that's a personal opinion.
Well,
And I'm running over.
yeah, thanks so much.
Thank you.
I'll be around later.